Welcome to the lecture on static single assignment form. We are going to study the construction of the form known as the SSA, static single assignment, and we will also look at a couple of applications of this form which are very useful in program optimizations. So, what exactly is the static single assignment form and what are its advantages? It is a new form of intermediate representation that is used in compilers. So, basically we still maintain the control flow representation, but the basic difference between a control flow graph and the SSA form is that it incorporates the definition use, def use information. So, because and the second important property which differentiates it from the control flow graph is that every variable has exactly one definition in the program text. So, I must hasten to add that it does not mean that there are no loops. There definitely are loops, otherwise there is no way you can write non-trivial programs. This is a static single assignment form and not a dynamic single assignment form. In other words, there will be definitely loops, and within the loop there will be exactly one definition for each variable. The loop may iterate, and at runtime the same variable may get many values, but when you look at the program statically, that is as the compiler sees it, the loop will have exactly one definition for each variable, and of course, elsewhere in the program as well there is going to be exactly one definition per variable. So, because of this property, some of the optimizations are going to be much simpler to perform, much more efficient, effective and all that. One very big advantage in using SSA form is on the constant propagation. So, we are going to look at constant propagation in great detail later, but conditional constant propagation and global value numbering are much faster and more effective on the SSA forms. So, in other words, the time required to perform the constant propagation is much smaller on the SSA form than on the control flow graph. And the global value numbering that we have already seen with basic blocks is performed with a little more effectiveness in the case of SSA forms. SSA forms are also known as sparse intermediate representations. Why? Why are they called sparse? If a variable has n uses and m definitions, then the def use chains require space and time proportional to n into m. So, this is fairly well known. So, you have m definitions and n uses. So, there may be intertwining among these definitions and uses. So, you will possibly require n into m amount of space and time to consider these def use chains. The corresponding instructions of uses and definitions are obviously only n plus m, because every definition is one instruction and every use is another instruction. So, you have n plus m number of instructions corresponding to these. The SSA form for most realistic programs is linear in the size of the original program. So, it does not require quadratic amount of space in either the number of edges or number of nodes in the graph. So, this is the basic advantage, and we will see later that the time required to perform constant propagation etcetera is also much smaller. So, let us look at a simple example and understand the features of SSA forms. Here is a program in non-SSA form, the usual programs that we write, and here is the SSA form. it is not as if the SSA form cannot be written in text mode. Okay, text forms of SSA programs are also possible, but it is easier to understand the salient features of these forms if they are shown in the form of a flow graph. So, read A, this is just a max finding program. So, read A B C, if A greater than B, then check A greater than C, if so max equal to A, otherwise max equal to C. So, else if B greater than C, max equal to B, else max equal to C. So, printf max. So, when this is in SSA form, so far so good, you start off, then read A B C, then check A greater than B, if so check A greater than C, then max 1 equal to A. Let me tell you what these max 1 etcetera are, otherwise max 2 equal to C. So, if B greater than C, max 3 equal to B, and otherwise max 4 equal to C. So, at this junction point, we have used only one variable called max, and it is being updated in the whole program at various points in time. But here in this SSA form, we are not allowed to have more than one definition per variable. So, these would have been max equal to A, max equal to C, max equal to B, max equal to C, etcetera. And then here we would have had printf max, but in the SSA form this is not possible. So, we have to introduce different variables. So, let us say this definition is max 1 equal to A, this is max 2 equal to C, this is max 3 equal to B, and max 4 equal to C. So far things have been very easy, but when we come to this merge box, the join node, we have 4 values of max coming from the 4 edges. Which ones are which particular value among these is relevant to us will be known only at runtime. So, if the control flow actually is along this path, then it is max 1, otherwise it is max 2, etcetera, etcetera. This choice is exercised by actually putting in place what is known as a phi function. So, a phi function has as many parameters as the number of incoming edges. So, we have max 1, max 2, max 3 and max 4. The semantics of this phi function are straightforward. So, the order of these parameters actually corresponds to the order of these incoming edges. So, the first parameter corresponds to the first edge, second parameter corresponds to the second, and so on. At runtime, the implication is if the computer is supposed to execute the phi function and has, let us say, hardware to do it, then if the control flow comes along this particular edge, the phi function returns max 1. If the control flow is along this edge, it returns max 2 and so on and so forth. So, appropriately this max phi, which is being assigned this phi function here, will get one of these values only at runtime, and thereby max phi will record the maximum of A, B and C. So, this is a simple example. We are going to see more examples. Let me show you one right away. So, for example, before that, let me give you a definition of an SSA form. Maybe some of the details are already here that I mentioned. A program is in SSA form if each use of a variable is reached by exactly one definition. So, I mentioned this already, every variable has exactly one definition, and this is static, not dynamic. Flow control remains exactly the same as in the non-SSA form. So, we saw that example already. A special merge operator phi is used for selection of values in join nodes. So, I showed you this join node and the phi operator. Not every join node needs a phi operator for every variable. So, this is important. Just because it is a join node and there are 3 variable values coming in, it does not mean we need 3 phi functions. There is no need for a phi operator if the same definition of the variable reaches the join node along all incoming edges. So, in other words, along these edges, if exactly the same definition, let us say there was a definition t equal to 5 here, then the same definition actually arrives along all the paths and reaches this point. There is no need to have different versions of t and a phi operator for t in this particular join node. That is what this is really saying. Often the SSA form is augmented with du and ud chains to facilitate design of faster algorithms. So, in the case of conditional constant propagation algorithm, we will need the du chain in order to make the algorithm much faster than others. Translation from SSA to machine code introduces copy operations which may introduce some inefficiency. So, you observed here that the phi operator is special and there will be possibly no machine which can execute this as a machine instruction. So, we need to convert the phi operator into ordinary machine instructions. So, we will see how this can be done a little later. But I should mention here that the conversion operation will introduce a few copy operations and therefore, there may be some inefficiency which is introduced, but hopefully the other optimizations such as copy propagation and register allocation will handle this inefficiency and it is not going to be very visible. Let us look at more examples. So, this program is almost a meaningless program. It is very similar to binary search in syntax, but not necessarily in semantics. It has been concocted to show the specialties of the SSA forms. So, here is SR equal to LSR plus RSR by 2 after initialization and reading A. Then we have a repeat until loop. You compute t equal to SR star SR, then if t greater than A, RSR equal to SR, if t less than A, LSR equal to SR, else LSR equal to SR, RSR equal to SR, and finally SR equal to LSR plus RSR by 2 until LSR not equal to RSR, finally print SR. So, the flow graph form of the program and the SSA form of the program are shown side by side to give you a good comparison. So, this is the initialization block and then you compute the initial values of SR as well and then so on t equal to SR star SR and so on and so forth. So, now this is a join point and this is again a join point, there are because there are multiple incoming edges here. So, each of these join points definitely has phi functions. So, observe that this t here is SR equal to SR, but the join node here has many phi functions. So, let me tell you why this is required. So, for example, this SR star SR, okay, when the control flow is through this will require this SR value which is computed in basic block B1 and when the control flow later on iterates like that, okay, it will receive SR value through this statement, okay, that is B8. That is the reason why you require a phi function for SR in this case. We will also see later how exactly to place these phi functions, but this is the first join node where the LSR value from B1 and the LSR value from these two, okay, the LSR equal to SR, this B6 and B7, they actually meet. So, the value either here, the value here and the value here will definitely require a phi function here and then that value in turn will be propagated to this basic block B2. So, that is what is shown here. So, LSR 5 okay, is mentioned here. So, that is actually from these for these two LSR 2 along this direction, LSR 3 along this direction and LSR 4 along this direction. Similarly, RSR there is one value coming through this and one other value coming through this and a third value coming through this. This may be a little puzzling, but phi function is also treated as a definition. So, that will again in turn give you a value. That is how we introduce phi functions and so on and so forth. We will see this later. So, this and this require phi functions for LSR, RSR and SR variables. So, now you can see that if the control arrives here, it is going to be LSR 1. If the control arrives along this path, it is LSR 5 corresponding to this. So, sorry, LSR 1 if it arrives here, that is the second argument, and LSR 5 if it arrives along this particular path. Similarly, for RS 2, if the control arrives along this path, it is RSR 1, and if it arrives along this path, it is RSR 5, etc., etc. There is a third example. So, here is the non-SSA form. It has two junction points 1, 2, B2 and B7. Each of these join points do not require phi functions for both I and n. B2 requires two phi functions, one for I, another for n, but B7 does not require any phi function for I, it requires a phi function only for the n. So, for example, here the value of I can come from here or from this I 3. Okay. So, that is why there is a phi function here. Similarly, the value of n can come from here or it can come from this n 5, n 6. So, whereas in this particular case we are only computing a new value of I 3 and we are not making a choice of I 3 which actually is arriving from this edge or this edge. The value of I 2 computed in B 2 actually arrives along both paths, and that is the reason why we do not require a new phi function for I in block B 7. So, this is the SSA form for this particular program, and the choice of values here along this path it will be n 3 and along this path it will be n 4. So, depending on which path we take during execution, n 6 will get that particular value. That is how the phi function operates. So, what are the conditions on the SSA form? After the translation process, in other words, we are given actually a non-SSA form program, and we will go through an algorithm which converts this non-SSA form program to SSA form. And after the translation, the SSA form should satisfy the following conditions for every variable v in the original program. So, what are these conditions? If two non-null paths from nodes x and y, each having a definition of v, converge at a node p, then p contains a trivial phi function of the form v equal to phi of v comma v comma etc., with the number of arguments equal to the in degree of p. So, what this says is the trivial phi function is of the form v comma v phi of v comma v comma etc., with all the variables being mentioned as v. The renaming operation making each of these distinct as v 1, v 2, v 3 etc., happens a little later in the algorithm, and when that happens, the rest of the properties will be satisfied. So, this simply says when two definitions converge at a node, then we require a phi function at that node. The second condition is each appearance of v in the original program or a phi function in the new program has been replaced by a new variable v I, leaving the new program in the SSA form. So, the phi function is also an assignment v equal to phi of. So, this v also needs to be changed into a new variable. So, that is precisely what this is saying. All the definitions will require to be changed to different variables, and this v equal to phi of etc. also needs to be changed into a new variable, but we must make sure that the new program is in SSA form. that is exactly one definition per variable. Any use of a variable along any control path in the original program and the corresponding use of V I in the new program yield the same value for both V and V I. So, this is making sure that the semantics of the program does not change when we change it to SSA form. So, the each instance of the variable which is in the definition will get a new variable name. So, that variable name should have the same value as in the original program at any control point. That is what this is trying to say. So, condition 1 in the previous slide, that is the trivial phi function placement, is recursive. It implies that phi functions, phi assignments introduced by the translation procedure will also qualify as assignments to V. So, this is what I was saying. So, you have to place phi functions and then look at them, treat that also as a new assignment to V. So, you have to introduce a new variable for that assignment as well. In fact, it may so happen that introduction of one phi assignment will lead to introduction of another phi assignment. I will show you an example in this particular case. So, see here, this particular phi function which is introduced here, LSR is because of these three edges, there are two LSR definitions coming in here, right. And this LSR function is fed here. So, now we have two LSR values come, one from here and another from here, and therefore, we will have to place a phi function for LSR in this case as well. So, like this, introduction of one phi function may require introduction of one more phi function and things of that kind, and that is precisely what this is trying to say. So, we have to go on collecting the phi assignments also as definitions and see if more phi functions become necessary because of these. We already saw that it is wasteful to place phi functions in all join nodes. So, some of them do not require phi functions. For example, here I does not require any phi function because the value of phi is the same along all paths. It is possible to locate the nodes where phi functions are essential. So, it is possible to compute through an algorithm and enumerate the nodes where phi functions are essential. So, this property is captured, this information is captured by the dominance frontier property. So, which we are going to study in some detail. So, let us understand what are known as join sets and phi nodes, the relationship between these, and then go on to the dominance frontier. Let us say we are given a set S of flow graph nodes, then what is join S? So, the join S is the set of all nodes n such that there are at least two non-null paths in the flow graph that start at two distinct nodes in S. So, you are given S and then you are picking two nodes. Both of them have definitions of variables that we will see later, but these are two distinct nodes and they have non-null paths in the flow graph that converge at n. So, that is what is important for us. The paths considered should not have any other common nodes apart from n. So, let us look at some simple examples. So, let us take B1, the set S is B1 comma B7. Okay. So, B1 and B7 here. We want to compute the join. So, read this as join, it does not matter, join plus will be defined very soon. So, from B1 let us look at some paths and then from B7 also let us look at some paths and see where they converge. We should take the first node where they converge. So, this goes to B2 and from B7 using the back edge we also arrive at B2. So, this is the first node where we converge. So, this is in the join set of B1 comma B7. What about B1, B5, B6? So, B1, B5 and B6. Let us take two at a time. Suppose you consider B1 and B5. So, B1 is here and B5 is here. So, from B1 we arrive at B2, from B5 we go via the back edge and again arrive at B2, that is the first node where they collide. So, B2 is in the join set of B1 and B5. Let us take B1 and B6. So, if you consider B1 and B6, you still end up with B2, because B1 comes to B2 and B6 also goes through B7 and then comes to B2. So, there is nothing more to be added here, but if you consider B5 and B6, the first node they converge to is B7. So, B7 is also in the set of join nodes. So, this is the way we compute join, rather define join. What is an iterated join set? Join plus set, yes. This join plus is needed to take care of phi functions introduced by phi functions. So, let us define it. So, recursion again. So, join 1 yes, this is the terminating condition equal to join yes, and join of I plus 1 yes is join of SU in join of I of S. So, you combine S and join I of S and take the join of that, then you get join I plus 1 yes, that is called as join plus. This is the closure. If S is the set of assignment nodes for a variable V, then join plus S is precisely the set of flow graph nodes where phi functions are needed for V. So, this is the reason why we wanted to define the join set. So, join plus S is termed as the dominance frontier D of S, and definitely it can be computed efficiently. So, we are going to look at some algorithm to compute the dominance frontier. So, the central concept in translating an ordinary flow graph to SSA form is the concept of dominance frontier. So, we need to understand how to define and compute dominance frontier. So, to continue with the same example, by adding B2 into B1 comma B7, that is S union B2, we really do not get any extras. So, if you take B1 and B2, it gives you nothing extra. Taking B2 and B7 also gives you nothing more. So, similarly, taking B2 and B7 into S and then computing join still does not add anything to this particular closure. So, we are going to actually look at the join plus as B2 comma B7 itself. Second example. So, again let us compute the join. Okay. So, we are looking at B1 and B8. So, B1 is here and B8 is the other join node. So, let us take only the join nodes, because they are the only ones which are of great interest to us. These are the only places where we need to place put phi functions. So, these two converge at B2, very similar to the previous case. So, this goes through this arc and then comes to B2. This is for the variable SR. For the variable LSR, let us consider the definitions where LSR is nodes where the LSR is defined. LSR is defined in B1 and then LSR is defined in B6 and it is also defined in B7. So, we are going to consider B1, B6 and B7 for that particular purpose. Now, we need to take 2 at a time. So, let us take B1 and B6. So, they actually we can take a path along this particular edge and come to B8, B6 directly comes to B8. So, B8 gets included. Remember, we are not supposed to use common paths, okay? They should be disjoint paths. They meet only at the common node. Then B6 and B7, B6 and B7 again meet at B8. What about B1 and B7? Okay. So, B1 again comes here and B7 also comes here. but then you know for the RS, suppose we add this B8 into B1, B6, B7, right. So, we have now added, we are taking S union this join. Okay. So, then B1 is here, B8 is the extra. So, B1 and B8 actually meet only in B2, that is how B2 comes into the set. Okay. So, B8 remains in the set, B2 and B8 now form the join plus. Similarly, the RSR, it is very similar. So, RSR is from B4 and then B1 and then B7. Okay. So, these three again will converge at B2 and B8, the join plus operation gives us B2 and B8. So, B2 and B8 are the places where we are going to place the phi functions for all the three variables, sorry, for both variables LSR and RSR, and SR will have one phi function in B2. Okay. So, that is how placement takes place. So, how do we compute the dominance frontier? To compute the dominance frontier, we require dominator information. So, let us do a recap on dominators that we studied a couple of lectures ago. Given two nodes x and y in a flow graph, x dominates y if x appears in all paths from the start node to y. So, that is the definition of dominator. So, if you look at this example, here is the dominator tree information for this particular flow graph. So, B2 dominates all these nodes, because all the paths starting from start node to any one of these nodes has to pass through B2, and B3 dominates B5 and B6, sorry, B3 dominates B5, B6 and also B7. The reason is if you look these two are very simple. So, every path from start goes through B3, but even to reach B7 you have to actually pass through B3. Neither B5 nor B6 will dominate B7, because you can always find an alternate path to reach B7 by passing the node B5 or B6. So, the node x strictly dominates y if x dominates y and x is not equal to y. So, this is one of strict domination. So, we do not want x equal to y. X is the immediate dominator of y, I dom, this is important for us, if x is the closest strict dominator of y. So, this particular tree information that is given here shows only I dom information, immediate dominator information. It does not show the transitive relationship, it should be inferred using the descendants of a particular node. So, B2 for example immediately dominates B3 and B4, but it also dominates B5, B6, B7 and stop, but they are all descendants, that is it. So, dominator tree shows all the immediate dominator relationships. So, now coming to the dominance frontier. So, we have defined the join set, so where two definitions converge for the first time. Now, dominance frontier is exactly that, but we are going to define dominance frontier in a structural way, so that computation is simpler. We are going to use dominator information for that. D of x is the set of all nodes y such that x dominates a predecessor of y, but x does not strictly dominate y. So, this is the definition of dominance frontier. So, it should dominate a predecessor of y, but x does not strictly dominate the node y itself. So, but this is still not a great definition if we want to compute it. So, let us first understand intuitively what exactly is this dominance frontier. It does not seem to be so clear. So, a definition in node n forces a phi function in join nodes that lie just outside the region of the flow graph that n dominates, hence the name dominance frontier. So, informally the set df of x contains the first nodes reachable from x that x does not dominate on each path leaving x. So, let us look at this example. So, if you look at start node, okay, it dominates every node. So, there is no question of reaching a node which is not dominated by start. Therefore, the dominance frontier which is indicated just beside the node here, okay, is phi for start. The same is true for B1. There is no node which cannot be, which is not dominated by B1, but is still reachable. Start is not dominated by B1, but there is no path to start node. Suppose you consider the node B2, right. So, B2 dominates again every other node here B3, B4, B5, B6, stop and B7, okay. But there is a path from B2 using the back arc back to B2. So, since we are looking at strict domination only, B2 dominates itself is not considered for us, in our algorithm. So, there is a path from B2 to itself through the back arc, and B2 does not dominate itself, okay, in the strict dominator sense. Therefore, the dominance frontier of B2 consists of the node B2. Let us consider B3. So, you are looking at B3 dominates B5, B6 and B7, B5, B6 and B7. So, let us start taking a path out of these, you again go to B2. So, this is B2, okay. Dominance frontier of B3 is also B2. Let us look at B5. B5 does not dominate any node. So, the immediate node which is reachable from B5 is B7, and that is its dominance frontier. The same is true for B6 as well. If you look at B7, it does not dominate any other node. So, the next node reachable is B2. So, it is B2. B4 dominates stop and there is no other back arc. So, B4 has dominance frontier as phi, and same is true for stop as well. So, this is what is explained in this particular slide. So, let us look at the second example. So, B0 and B1 are similar. They have dominator information, dominance frontier information as phi, because start and B1 dominate every node in the flow graph, and no other node is reachable from either start or B1. That is, no other node which is not dominated by them is reachable from these two nodes. B2 again, because of the loop, is reachable from itself. So, its dominance frontier is B2. The same is true for B3. So, you go through this path, right, and then the first node you come to is which does not dominate is B2. So, the dominance frontier for B3 is also B2. What about B4? B4 is here and it does not dominate any other node. So, the next node is B8 and hence DF is B8 for B4. Similarly, for B5 as well, DF is B8. So, it dominates B6 and B7. Okay. It comes here. This is not dominated by B5 because there is a path like this. So, B8 is on the dominance frontier of B5, and for B8 itself, we again it dominates all other nodes here, B10, B9, B10 and B11. So, we reach B2 and that is in DF. For B6 and B7, it is just B8, and then for B9 you again can go back. So, it is B2 and for others it is phi. So, this is how the dominance frontier information is intuitively understood. So, you are really looking at the node just immediately beyond the nodes which are dominated by the particular node, and that is why it is some kind of a frontier just beyond the dominator region, and then it is called a dominance frontier. How do we compute the DF? Whatever we said so far is not an algorithm, it is only an intuitive explanation of what DF is. Algorithm is simple. Identify each node x in the flow graph. For each predecessor p of x in the flow graph, traverse the dominator tree upwards from p till I dom of x. So, during this traversal, add x to the DF set of each node met. So, let us walk through our examples and compute the DF information accordingly. So, again we really need to consider only the join nodes B 2 and B 7. If you compute the DF information for them using this algorithm, automatically the DF information for all others also gets computed. So, let us see how. So, the algorithm says identify each join node. For each predecessor p of x, traverse the dominator tree upwards from p till you reach I dom. So, we are in B 1. Okay. So, let us say we are in B 2 because that is the first join node that we have. There are two predecessors in the control flow graph for this node B 2. So, go to the dominator tree, look at B 1. B 1 is indeed the immediate dominator of B 2. So, we do nothing, we have to stop, we cannot go beyond the dominator, immediate dominator. So, you come to B 7. Okay. So, B 7 is here, and now we can traverse to B 3 and the B 2 and then to B 1, that is the point where you stop. And as we go on traversing these parents in the dominator tree, we are going to add the node B 2 as to the dominance frontier of each node that we meet in the dominator tree. That is what this is saying. During this traversal, add x to the DF set of each node met. So, start with B 7, add B 2 to its DF, go to B 3 its parent in the DF dominator tree, add B 2 here, go to B 2 the parent of B 3, add B 2 there as well, and then go to B 1, that is the I dom of the B 2 here. So, you stop. So, now we have looked at both the paths for B 2. Let us look at the node B 7. This is the other join node in the graph. It has two predecessors B 5 and B 6. So, let us go to B 5 first. So, we can start from B 5 and then the immediate dominator of B 7 is B 3. So, in one step we reach B 3. So, we can only add the node B 7 to the DF information of B 5 and then we go to B 3 and then we need to stop, we can't do anything more. Similarly, from B 6 we add B 7 to the DF information of B 6, go to B 3 and then we stop. So, this is how dominance frontier is computed in as an algorithm. So, observe that whatever is left over, all others are phi. Well, you can actually start from some other node. Let us take for example, B 4. Okay. So, B 4's predecessor is B 2, right. So, B 4's predecessor is B 2, but B 2 also happens to be the immediate dominator of B 4. So, there is nothing you can do there. So, this is how all other leftover nodes actually get phi. Okay. Others have been filled up already. So, this is also a very interesting flow graph. It has two join nodes. So, let us look at B 2, which is similar to the B 2 in previous case. This also has two predecessors B 1 and B 9. If you look at B 1, it is the immediate dominator of B2. So, nothing gets added. So, we go to B9. From B9 you can go on adding the node B2 to every one of these parents. Okay. So, you have added it to B9, you have added it to B8, then you go to B3, you have added it to B3, then you go to B2, you have added it to B2 as well, then you go to B1, it is time to stop. Why? B1 is the immediate dominator of B2, therefore, we need to stop. Now, we have covered both the paths, both the predecessors of B2, one is B1, the other is B9. There is one more join node, that is B8. B8 has many predecessors, one is B4, the other is B6 and the third one is B7. So, let us start from B4. So, if you are somewhere here, so in from B4 you can add B8 to it, then you go to B3. So, B3 is the immediate dominator of B4. So, you need to stop. Then the other predecessor is B6. So, B6 is here. So, B6 you add B8 to it, go to its parent, add B8 to it, then you go to B3 which is the immediate dominator of B8. So, you need to stop. The same is true for B7 as well. You add B8 here, go to B5, nothing to be added, and then you go to B3 and you need to stop. So, this is because for B8, okay, B3 is the dominator, immediate dominator, and we need to go up to that point only, nothing beyond that. So, we have covered all the three predecessors. No, B7 is remaining, sorry. So, you start B7, we go to B7, add B8, B5 we add B8 and then we go to B3 and we need to stop. So, we have covered all the three predecessors of B8 and we have actually added dominance frontier information for all these nodes. The rest are all going to be phi. So, we saw the algorithm on the example. So, let us look at the algorithm in the algorithmic format. So, for all nodes n in the flow graph, initialize the dominance frontier to phi, that is it. So, to begin with we have already initialized to phi. So, these will remain as phi, all others will get modified. Then for all nodes n in the flow graph do. So, actually as I mentioned, it is enough to consider only join nodes, there is no need to consider other nodes at all. Other nodes automatically get their DF sets on the way during this process. Now, the main loop is here. For each process predecessor p of n in the flow graph do, say store t equal to p, then go on till idom n. So, t not equal to idom n do. So, add to the df of t the node n. Okay. So, df of t union n and then go to the parent t equal to idom of t. So, this keeps happening until you go to the immediate dominator of the node n. So, on the way you have updated all the df nodes, df sets with n. So, now we are ready to discuss the construction of the static single assignment form. So far we have learned how to compute the dominance frontier information for each node in the flow graph. So, I compute using that algorithm. For each variable v, place trivial phi functions in the nodes of the flow graph using the algorithm place phi function v. rename the variables using the algorithm rename variables. So, these are the 3 concrete steps in the construction of the minimal SSA form. Why is it called a minimal SSA form? A non-minimal SSA form would possibly place 5 functions which are redundant. It will just place it in every join node for every variable which enters that node, and some of these are redundant. Whereas, this minimal SSA form places 5 functions in only those nodes, join nodes, where it is essential. So, what is the outline of the placement 5 placement process? So, we are going to look at the more detailed version of the algorithm, but let us first get the outline. The 5 placement algorithm picks the nodes with Ni with assignments to a variable. So, there may be many nodes which assign to a variable v. So, each of these nodes is picked up. It places trivial 5 functions in all the nodes which are in the df of Ni for each I. So, if there are 3 nodes where an A is being assigned, a variable A is being assigned, look at the dominance frontier of each of these nodes, go to the df node and place a trivial 5 function there. Trivial 5 function is of the form phi of v comma v comma v, etcetera, etcetera, and the number of operators for operands for the 5 function is equal to the number of predecessors of that particular join node. This process uses a work list, that is a queue. So, let us look at an example to understand how it works and then go to the details of the algorithm. So, here we have in the original example we had a statement I equal to and n equal to and here we had n equal to and I equal to. So, these are the 2 join nodes that we had seen. So, when we place 5 functions, the trivial function implies I equal to phi of I comma I. So, we want to choose I, but we have still not renamed the operands of the 5 function, that is why this is called as a trivial 5 function. Similarly, n equal to phi of n comma n. So, we had an I a statement I here and we had a statement I here. So, the dominance frontier of each of these nodes is just this. So, we placed a 5 function for I here. There was a statement n equal to in this node and also in this join node, right. So, the dominance frontier of these happens to be this and this. So, sorry, there was a statement read n which is an assignment to n here. There is another statement n equal to something here and n equal to something here. So, the dominance frontier of all these happens to be this node and this node. So, we need to place 2 trivial 5 functions in these 2. So, there is an n equal to phi of something and n equal to phi of something here. Similarly, for I is assigned here, I is assigned here. So, the dominance frontier of this B1 and B7 is B2, that is why there is a trivial 5 function for this in this particular node. No other node has any trivial 5 functions. So, algorithm is simple. So, let us study the algorithm in some detail. So, place-phi function, v is a variable. This says the function is executed once for each variable in the flow graph. So, there is a has phi b which is a predicate. It is true if a phi function is already been placed in B, and process b is another predicate which is true if b has already been processed once for variable v. So, there is initialization for all nodes has phi b equal to false and process b equal to false. So, the work list begins with phi and then assignment nodes v is the set of nodes containing statements assigning to v. So, for all nodes b in assignment nodes v, process b is true and add it to the work list. Now, pick up a node from the work list. If it has not for all nodes y in the dominance frontier of B, if it does not have a phi function correspondingly for this particular variable, place a trivial phi function there, make has phi true. If y has not been processed, now assign it processed equal to true, add this to the work list. This is where some explanation is necessary. This last statement add w comma y implies that the new phi statement which has been added to the program may cause more phi statements to be added to the program, and that is the reason why we are adding it to the work list. So, one by one the nodes where assignments to the variable v are made is taken out of the work list, its dominance frontier is checked. For each of the nodes in the dominance frontier, we place a trivial phi function. So, if these nodes have all not been processed, the ones in which phi functions have been placed, they are added to the work list once again, and the entire process continues until the phi function until the work list becomes empty. So, this is the example we have seen. So, I equal to 0 and I equal to I plus 1 are the two nodes. Look at the dominance frontier, that is here. So, add a phi function here, but then processing this will not yield any more phi functions. So, similarly read n, n equal to n by 2, n equal to 3 star n plus 1 are all nodes where we require we have an assignment to n. So, look at the dominance frontier of these. So, those are these two places. So, we have added trivial phi functions in these two places, but these two together again do not yield new nodes where phi functions have to be assigned. So, that is how phi functions are assigned. Let us stop the lecture at this point, and in the next lecture we will take up renaming of variables. Thank you.